What's up guys, welcome back to a new video where we learn about mathematics and physics by doing exercises step by step. In this session, we'll be focusing on how to calculate the inverse of a 2x2 and 3x3 matrix. Because a lot of students struggle with this topic, I will be solving these exercises in a systematic step-by-step approach which reduces the chances of making mistakes. In addition to this, I will be showing you a trick that allows you to check whether you got the right result or not, so that you can correct yourself if needed. If you want to skip right ahead to the 3x3 matrices, you will find the timestamps of each exercise in the comment section below. And with that, let's get into the first exercise. In this first exercise, we want to calculate the inverse matrix of this 2x2 matrix. The first step is to calculate the determinant of this matrix, which in this case simply is the determinant of this 2x2 matrix, which we know how to solve. And if you're uncertain on how to calculate this determinant, I gladly refer you to my other video where I show you how to calculate 2x2 determinants. Basically, we multiply these two elements and we subtract the product of these two elements. This means that we get 1 times 2 minus 5 times 2, which is of course 2 minus 10, which is minus 8. And the first step is already down. The second step is the step where most people make mistakes, and it's to actually calculate the inverse matrix. The inverse matrix is equal to 1 over the determinant, which we already calculated, times a 2 times 2 matrix, which we need to transpose. And this transposition of this matrix is basically swapping the rows and the columns. But this we will leave for a further step because we don't want to do all of the things at once, just to reduce the chances of making mistakes. So in this step, we will just focus on getting these 4 elements of this 2x2 matrix. How do we get these elements? Well, for this element on the first row and first column, we ignore the first row and first column of our initial matrix, and the element that we are left with is the element that comes on this place. So in this case, it becomes a 2. Then for the element on the first row and second column, we ignore the first row and second column, and we are left with this element here, this 5. However, I'm drawing this in red because on this position, we need to also add a minus sign in front of this element, which is the same than the element on this position, the second row and first column. We ignore the second row and first column, and we are left with this 2 right here. But also here, we have to take into account that we need to add a minus sign in front of it. And then for the element on the second row and second column, we ignore the second row and second column, and we are left with this 1 right here, which just can be copied right here. The reason of these minus signs, I will leave for a theory video. However, the important part here is that it has this pattern of alternating signs. So we have plus, and on the off diagonal, we have a minus and minus. Right now, let's just calculate this matrix. So we have 1 over d, and d is minus 8, times the transpose of this matrix, which means that the rows will become columns, and the columns will become rows. For the first row, we need to look at the first column, which in this case becomes 2 and minus 2. And for the second row, we will have to look at the second column, which in this case becomes minus 5 and 1. And there you have it. We already have our result. This is officially the inverse matrix of our initial matrix. Now, I said that I would also give you a trick to see whether you indeed calculated the right matrix. And let me do that right now. To do this, we need to think, what is the inverse matrix? Well, it's defined by the fact that if you multiply your initial matrix with the inverse matrix, that you just get the unity matrix, which for 2x2 matrices is 1, 0, 0, 1. So if we multiply our resulting matrix with our initial matrix, we should get 1, 0, 0, 1. And this is exactly what we're going to do now. So we multiply the initial matrix, 1, 2, 5, 2. And we multiply it by minus 1 over 8 times the matrix that we calculated, 2, minus 5, and 1. And this should be this matrix right here. So let's see whether that's the case or not. I will be going over this matrix multiplication only once in this session because I already made an extended video on how to multiply matrices step by step. The element on the first row and first column we achieve by multiplying the first row of this matrix with the first column of that matrix. So we get 1 times 2 plus 2 times minus 5. For the element on the first row and second column, we multiply the first row and second column, and we get 1 times 2 plus 2 times minus 2. For the element on the second row and first column, we multiply the second row and first column, and we get 2 times 5 plus 2 times minus 5. Then for the element on the second row and second column, we multiply the second row and second column. And we get 5 times minus 2 plus 2 times 1. Making these little sums, we get minus 1 over 8 times 2 minus 10 is minus 8. Minus 2 plus 2 is equal to 0. 10 minus 10 is equal to 0. And minus 10 plus 2 is minus 8. And if we now multiply these elements with this factor in front of it, we indeed get 1, 0, 0, 1. So our matrix that we found, our inverse matrix, is indeed the inverse of this matrix. Let's go to the next exercise, which is to find the inverse of the matrix minus 3, 2, 0, minus 3. So what is a to the power of minus 1? Again, the first step is quite straightforward. It's just calculating the determinant, which in this case is the determinant of minus 3, 2, 0, minus 3. And it is again equal to the product of these two numbers minus the product of these two numbers. So we get that this is minus 3 times minus 3 minus 0 times 2. And this is of course equal to 9. The second step is the, well, a bit more complex step, but if we just follow the systematic approach, we will get the right answer. We know that the inverse of A is equal to 1 over the determinant, which we already calculated, times a 2 by 2 matrix, which we have to transpose. Let's first focus on getting these 4 elements. Again, the element on the first row and first column, we get by ignoring the first row and first column, and the element that remains is the element that we need, minus 3 in this case. So we simply have minus 3 here. Then the element on the first row and second column, we get by ignoring the first row and second column and putting a minus sign in front of the element that remains. In this case, it is 0, so we have minus 0. Then again, the element on the second row and first column, we get by ignoring the second row and first column, looking at the element that remains, a 2 in this case, and putting a minus sign in front of it, so minus 2. And then the element of the second column and second row, we get by ignoring the second column and second row and copying the element that remains, and this is a minus 3 in our case. And at this point, the most difficult part is over already, because now we just fill in the determinant, which is 9, so we get 1 divided by 9 times the transpose of this matrix, which means that to get the first row here, we need to copy the first column over here. So we get minus 3, minus 2. And for the second row here, we look at the second column here. So we get 0 and minus 3. And this is already our result. And again, we want to check whether we made any mistakes. So we simply multiply our initial matrix with the matrix that we calculated, and we see whether we get the unity matrix. This means that we have to calculate the multiplication of this matrix times 1/9 of this matrix, -3, -2, 0, -3, and see whether this indeed gets us the unity matrix. And I will now go a bit more faster over this matrix multiplication. So we get, for the first element, that we multiply this row and column. So we get 9 plus 0. Then we multiply this row with this column. So we get 6 minus 6. Then we multiply this row with this column, which is 0 plus 0. And to end off, we multiply this row with this column, and we get 9 again. And we see, if we now bring this 1/9 inside, because this term and this term drops out, we get indeed 1, 0, 0, 1. And we see that we didn't make any mistakes. So our result, this matrix, is indeed the inverse of our initial matrix. And that's how fast these exercises can go without making any mistakes. The next exercise has a surprise for us. So let's see what it is. We need to calculate the inverse of the following 2x2 matrix. 6 minus 3 minus 3 plus 1/2. Step 1 is to calculate the determinant. And in this case, it becomes the determinant of 6 minus 3 minus 1, 1/2, which is equal to, again, the product of these two numbers minus the product of these two numbers. So we get 3 minus 1 times minus 3 is plus 3. So we get 3 minus 3, which is equal to 0. And if you watched my previous video on determinants, you know that we could have already seen this beforehand, because this row is exactly minus 6 times this row. And if one row or column is the multitude of another one, then the determinant will always be 0. The second step is to calculate the inverse matrix. So we get a to the power of minus 1 is equal to 1/d times this matrix that we need to calculate transposed. And again, to get some more practice, this element we get by ignoring this row and just copying this 1/2. So we get 1/2 on this element. For the element on the first row and second column, we ignore the first row and second column. We get this minus 1, and now we have to put a minus sign in front of it, so it becomes minus 1, which is plus 1. The element on the second row and first column, we get by ignoring the second row and first column. We get this minus 3, but we have to remember that we put a minus sign in front of it, and minus 3 becomes plus 3. And the element on the second row and second column is in this case just a 6. And now we calculate this, but we see that 1/the determinant, we get 1/0, because the determinant is 0. So it doesn't really matter what this matrix is. We get 1/0, which is ill-defined. This simply means that this matrix doesn't have an inverse matrix. There is no matrix which we can multiply this with that we get 1 in the end. This simply doesn't exist. And why is this? It is because this row is minus 6 times this row. So if we have a matrix of which one row or column is the multitude of another row of column, we can directly say that the inverse matrix does not exist. And we will save us a lot of calculations. So keep this in mind while we go to the next exercises, which are the exercises on the 3x3 matrices. The first exercise on the 3x3 matrices is to calculate the inverse of this matrix. 1, 3 minus 2, 0, 6, 2, minus 1, 0, 4. Again, the same steps apply. So we are not doing anything new here. It just becomes a bit more calculation work, but the same steps apply either way. Step 1 is calculating the determinant. And the determinant of a 3 times 3 matrix is a bit complicated, and I covered this in much detail in previous videos. So in this video, I will be calculating it a bit quickly, but still say all the steps that I do. So we get 1 times the determinant if we ignore this row and this column. So we have 1 times 6204 minus this number times the determinant if we ignore this row and this column, which is 0, 2, minus 1, and 4, plus this number and the determinant of the remaining elements if we ignore this row and this column, which is plus minus 2 times 0, 6, minus 1, and 0. And this simply becomes 1 times 24 minus 3 times 2 minus 2 times 6, which is equal to 24 minus 6 minus 12 is equal to 6. And we already have our determinant, which is the first step in calculating the inverse of this matrix. The second step is the more complicated step, but we will do it very slowly and I will explain exactly what happens. So again, the inverse of this matrix is 1 over the determinant times now a 3 times 3 matrix, which we have to transpose. And now let's get the elements of this 3 times 3 matrix. Again, so this element on the first row and the first column, we get by taking the determinant of the elements that remain if we ignore the first row and first column. In this case, it's the determinant of these 4 numbers, which is 24. So this first element will be 24. Then the element on the first row and second column will be the determinant once we remove the first row and second column. And the determinant of these numbers that remain is equal to 2. However, because this is a red element, we have to put a minus sign in front of it, so we get minus 2. Then again, for the element on the first row and third column, we get by ignoring the first row and third column and taking the determinant of the elements that remain. And in this case, that would be 6. And because it is a blue element, we don't have to put any minus sign in front of it. Let's look at the element on the second row and the first column. Again, we get this by ignoring the first column and the second row. And we have to take the determinant of the numbers that remain, which are these ones. And the determinant in this case is 12. And because this is a red element, we have to put a minus sign in front of it. So we get minus 12. The element on the second row and second column, we get by ignoring the second row and second column and taking the determinant of these 4 elements, the elements that remain, which becomes 4 minus 2, which is 2. Then the element on the second row and third column, we get by removing the second row and third column, looking at the determinant of the remaining numbers, and putting a minus sign in front of it because it's a red number. And in this case, this would be 3 with a minus sign in front, so it would be minus 3. The element on the third row and first column, we get by ignoring the third row and first column, calculating the determinant of the elements that remain, and in this case, that would be 6 minus 12, so plus 12, so 6 plus 12, which would be 18. Then we get a red number again on the third row and second column, which we get by ignoring the third row and second column. So we need to calculate the determinant of these 4 numbers, which is simply 2. But because it's a red number, we put a minus sign in front of it. And then the last element on the third column and third row, we get by ignoring the third column and third row, and getting the determinant of these remaining 4 numbers, which is simply 6 in this case. So we did now the most complicated part, and we can now go to the next step, which is taking the transpose of this matrix. So we should not forget this 1 over 6, which is 1 over the determinant, times the matrix that we get by swapping rows and columns. So for the first row, we actually get the first column. So we get 24 minus 12, 18. For the second row, we look at the second column, which becomes minus 2, 2, minus 2. And for the third row, we look at the third column, which becomes 6, minus 3, and 6. And we already have our solution. This is our solution of this 3 by 3 matrix. Now, because in this step, there is a large likelihood of making a small error, a minus sign, we want to check whether we indeed have the right result. And to do this again, we multiply this matrix with our inverse matrix, and we want to get the identity matrix, which in this case is a matrix with only ones on the diagonal. So we get that we have to multiply these 2 matrices, where I also multiplied this factor in front of it with each element of the matrix. So that's why this matrix looks a bit different, but it is the same matrix. Again, now we have to multiply these 2 matrices. And to do this, I also refer to my previous videos where I go into depth into how to multiply such matrices. So I will be going a bit more quickly here. To calculate the element on the first row and first column, we multiply the first row and the first column, which gives us 4 minus 1 minus 2, which is of course 1. For the element on the first row and second column, we multiply the first row and the second column, which we get minus 2 plus 1 plus 1, which is of course equal to 0. The same can be done for these elements, which we get 3 minus 1 minus 2, which is again 0. Then for this element, we multiply this row with this column, and we get 0 minus 2 plus 2, which is 0. And now we expect a 1 for this element on the second row and second column. So we multiply these 2, this column and this row, and we get 0 plus 2 minus 1, which is indeed 1. So it's starting to look quite good. For this element, we multiply the second row with the third column, and we get 0 minus 2 plus 2, which is indeed 0. Then for the third row and first column, we multiply the third row and first column, and we get minus 4 plus 0 plus 4, which is minus 4 plus 4, which is 0. For the element on the third row and second column, we get plus 2 plus 0 minus 2, which is of course 0 again. And then for the last element on the third row and third column, we get minus 3 plus 0 plus 4, which is minus 3 plus 4, which is equal to 1. And there we have it. So our check checks out. So we know that this matrix, which we calculated, is indeed the inverse of this initial 3 by 3 matrix. For the next exercise, we will see that this is quite an easy and fast exercise. And this looks at when we have to calculate the inverse of a matrix which only has elements on the diagonal. So what would the inverse matrix be of this initial matrix? Well, step 1 is to calculate the determinant. And the determinant of a 3 by 3 matrix with only elements on the diagonal is actually just the multiplication of all the elements on the diagonal. In this case, that will be -1 times 5 times -1, which is simply 5. Now, if you don't believe me at first, you can just calculate this as we did before. Step 2 is simply using the formula. So a to the power of -1 is 1 over the determinant times the matrix that we have to transpose. And this matrix actually becomes quite simple in this case. So let's go over it. The element on the first row and first column we get by taking this determinant, which is -5. -5. This element we get by ignoring this row and this column. And the determinant of these remaining numbers is simply 0. So we get 0. The same can be said on the element on the first row and third column, because this determinant is again 0. So this is starting to look quite nice. The element on the second row and first column we get by doing this, and we get again that this one is 0. Then the element on the second row and second column we get by removing the second row and second column, and here we actually get the determinant is -1 times -1 is +1. And then again, this element on the second row and third column, we remove the second row and third column, we see that again is 0. The element on the third row and first column is again 0. The element on the third row and second column is also 0, because the determinant of these 4 numbers is 0. And as last, the element on the third row and third column is the determinant of these 4 numbers, which is -5. What we do now is take the transpose of this matrix and fill in the determinant, which is 5. So for the row, we look at the column. In this case, the first row becomes -5, 0, 0. For the second row, we look at the second column, which becomes 0, 1, 0. And for the third row, we look at the third column, which becomes 0, 0, -5. And if we multiply this 1/5 with each of the elements in the matrix, we simply get -1, 0, 0, 0, 1 over 5, 0, 0, 0, -1. And we see that our result actually just is our initial matrix, but now each element on its own is inverted. So 1 over -1 is -1, 1 over 5 is 1 over 5, and 1 over -1 is also 1 over -1. If you have to calculate the inverse matrix of a matrix with only elements on the diagonal, you can simply just invert each element on the diagonal separately, and you will already have your matrix. Now for the last exercise, will also be quite quick if you remember something that I said earlier in this video. This matrix would be -1/2, 3, 8, 11 -7 over 8, 2, 1 -6 -16. So you might be inclined, okay, I know now how to calculate inverse of matrices, so let me just start with step 1 is taking the determinant and then go to step 2 and I will get my result. Yes, that you will get the result indeed. However, I want you to first have a look at this matrix and see if you notice anything strange or anything specific. Let's, for example, look at this row and this row and see if you can spot anything. For example, to go from 8 to -16, we have to multiply by -2. But wait a minute, from 3 to -6 is also multiplied by -2, and from -1/2 to 1 is also multiplied by -2. So we see that these two rows are connected by multiplication. And if you remember what I said with the last exercise of the 2 times 2 matrices, then we know that this matrix does not have a inverse matrix. And why is this? Well, because of the determinant, if you calculate it, it will be 0, because exactly these two rows are connected by simply multiplying by -2. And if the determinant is 0, then that means that there is no inverse matrix. So this saved you a lot of calculation because of the determinant being 0 and there is no inverse matrix. This brings us to the end of this session. And I really hope that at this point you are a bit more familiar with calculating inverse of 2x2 and 3x3 matrices. Now I know that this remains a very tedious exercise, but if you just break it up in enough steps, then the chances on making mistakes become minimal. If you like this video, give it a like. If you want to get notified by future uploads, subscribe, and I will see you guys in the next video. Bye.